Hello and welcome back to the channel. So we are going to do a buckling analysis using Ansys. So as you know, buckling is a condition when structures fail due to compressive loads. The dynamics of buckling cannot be captured by a normal static structural analysis or a transient analysis because that is defined by several other theories like the Euler Column Formula. So we'll move forward. Like in this simulation, I'm going to analyze a column that is of a T-shaped cross section. So in this case, I'm going to analyze this using three different element types: solid, beam, and shell elements. So initially, if we do it using solid elements, what we have to do initially is we have to model this in whatever the platform you like, SolidWorks, AutoCAD, or whatever. When we need to do it using solid elements, we don't have to consider anything. We just have to model this the structure completely. So that means a solid model. And then once you import such a geometry, the Ansys solver will automatically apply solid elements. You can just extrude it. You can just draw a T shape and then extrude it, and then obtain the solid model, and that's what you need to obtain the geometry. And then once you have the model, what you need to do is open up a static structural workflow, apply the material, right click on geometry and import the geometry as a step file, or if you have done it using space claim, that's fine. And once you double click the model, you'll get it here. And then what you have to do is initially mesh the geometry. Since this is a T shape, it's a general shape, so the mesh is a map mesh using hex elements or rectangular or square elements. I've used a body sizing here of 15 millimeters to apply a bit of refinement. So initially what you have to do is then apply the boundary conditions. As you know, for buckling, there are different end conditions. In this case, I'm simulating a fixed one end free and one end fixed condition, which gives us a equivalent length of 2L, if you know the theory of Euler Column Formula. So I've applied a fixed support on the bottom surface and a force of 50,000 newtons on the top surface. So buckling is compression. So you have to make an eye here when applying the load. You have to apply it in the direction of compression. You have fixed it here. The direction of compression is negative y direction, so that's why I've added a negative in the y direction. You can select components here and then apply in the respective direction. And once you solve it, you can just play the animation here of a total deformation. You can see this is just only vertical compression. You can't see any buckling loads or buckling dynamics here. So that's why I mentioned that we need a separate solver for this. So then what you can do is you can right click on this static structural solution, transfer data to new CAD and select eigenvalue buckling. Then something like this will appear. All these connections will automatically come. You don't have to worry about them. Don't worry about the other things here as well. So once this is there, you can double click on setup, and then you will get a similar window where you'll get the eigenvalue buckling setup right here. So in this case, you don't have to do anything. You have already applied the boundary conditions. The mesh is there. You just have to solve it. The default is of the solver is to find 2 modes, but if you need more than 2 nodes, you can change it from here. And then once the solution is done, you can obtain a total deformation plot. and then play this. This is the first mode. This is the first buckling mode. So if you see right here on the right corner, you can see the load multiply value. So this is a multiply value. So if you multiply the force applied, that is the 50,000 or whatever the force in your case. If you multiply it by the first mode value here, you will get the first critical load value of the first mode of buckling. If you multiply the load by the second multiplier, then you will get the critical load for the second mode. So that's how it's usually done. If you want the mod plot of the second result, you can click on this and then right click, create mod shape results, evaluate result, and you will get the second mode. If you can't see any deformation, then rotate around the axis, because like this is a 3D model and you will get buckling modes on all the directions. So make sure you rotate around and see. So yeah, that's it for the solid elements. So moving on for beam elements, you can similarly open up a static structural, and then since you're using beam elements, I created the geometry in this case using design modeler. You can open design modeler. Since the column is straight, I initially sketched a line of the length of the column, and then I created the lines from sketch from here, and then that gave me the line body here. Then I went to concept, cross sections, and T section, and I created the T section using my values here, 30, 120. You can see this. Once you have created the cross section, you can go to line body and you can assign the cross section here. So this is basically how you create a line body and assign cross sections, and this is how you create beam elements in a Ansys Workbench model. This is the only way, as I know, like except for Ansys APDL commands and Ansys mechanical APDL, there's no other way to change the element types. Like you can change the triad or hex types, but you can't change the beam or solid element or whatever the other types. So if you want to, you'll have to go this way, or else apply APDL commands. So once you have done it, close the design model. And similarly, as we did using solid elements, we can set up. Again, similarly, apply the materials. The cross section you can see here, apply a mesh. In this case, it's just a line, so it will come as a edge sizing, not as a face sizing or a normal refinement. And then you have to similarly add a force and a fixed support. In this case, as I told you, it's a line, which is basically how beam elements are applied. So the fixed and the force should be applied on the vertices. You can do that by going to vertices selector and select the top and bottom vertices, and then do as we did as the solid elements thing. Run the static structural simulation, and then transfer the data to eigenvalue buckling thing, and you can see the total information and the multipliers. You can see the first mode. So moving on to shell elements, what we can do is, let me open the model. I hope you guys know how to create surface bodies like this. The thickness is not defined. You just create a normal sketch and create a surface. You can do this easily on SolidWorks and also in Ansys as well. What I've done is here, I have created the normal surface body on SolidWorks, imported as a step. And once you open the static structural solver, you'll get 2 question marks in front of these bodies. That's because the thickness is not defined. So what you have to do is give the thickness values here and the material properties. You can select the material, whatever. The default is structural still, but I've added another material here. Then you can apply a face sizing or edge sizing here, because we have edges and faces as well. And since this was model using a surface model, the 2 surfaces are counted as 2 parts. So what we have to do is we have to join them. So in that case, you can right click on mesh, insert manual mesh connection, and then you can connect the 2 bodies. Like here I have selected this face as a master body and this edge as a slave body, and then connected them. You can use whatever the boundary conditions or the connection conditions depending on your model. And then similarly, we have to add the boundary conditions, poses and the fixed support. In this case, we have only edges. In the solid model, we had faces. In the beam model, we had vertices. In this case, we have edges. So apply the boundary conditions respectively. And then similar to what we did earlier, we have to solve the static structural work, the solver, and then transfer the data to eigenvalue buckling thing, and similarly solve the thing. Here you can also see the multiplier. So if you compare the multiplier values of the 3 elements types, I mean solid, beam and shell, the solid elements will give you the best results. One reason is shell elements can only be used to model geometries where one dimension is very small compared to the other. For example, like fins in heat exchangers or coolers. In our case, the thicknesses are not small compared to the other dimensions. So these are thick branches. So that's why the results are not that accurate. Similarly, in beam elements, the axial loads are not accounted. That is something that's a property of beam elements if you know the theory of finite element analysis. So yeah, the best results are given by the solid elements. So if you know the Euler column theory, you can do the theoretical calculation and check which values are which elements give you the best or the closest results to the theoretical values. So thank you. Yeah.